It's Space Radio. This is Paul Sutter, and coming up, we're talking about Good Night, Sweet Spitzer. And of course, taking listener questions about all things in this beautiful universe, because that's exactly what this show is about. We record every Thursday at 8 p.m. Eastern. You can follow along online or leave a voicemail at spaceradioshow.com. And in today's Blue Shift, I'll be talking about science is wrong. And that's just right. But first, the news. Hello, Space Cadets. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Stony Brook University and the Flatiron Institute. And for the next half hour, your agent to the stars. Got an amazing show for you today where we talk about all the amazing things in this universe. Surprisingly short program given the topic. This show lives on listener questions. We record every Thursday at 8 p.m. Eastern here in Spaceman Studios in New York City. So leave a voicemail at spaceradioshow.com to get yourself on the air. You can also follow along with our Space Cadets, tuning in live from around the world, including but not limited to London, UK, London, Canada, different London, Idaho, Texas, Ashburton, New Zealand, Washington, D.C., somewhere in South America, Pell City, Alabama, Southeast England, and Pittsburgh, PA. Thank you, Space Cadets, for tuning in live. You can follow along with them on YouTube or Twitch. Go to spaceradioshow.com for the links. We'll send questions. In fact, today's going to be an all Space Cadet all the time kind of show. Seriously, folks, I prepped like 2 minutes tops of material. That's all I got. That's all I got today. So get those questions in. You're going to hear a lot of that, Space Cadets. I got a cold, powering through it for you, for the love of science, for the love of space. Brexit denier. Wow. We're going to do all Space Cadet questions. It's going to be a fun show. I may not get as loud as I normally do, but that is okay. We are still going to be happy with that a show is even happening. Right? Right. Right. Also, a lot of water drinking will be had. And a lot of sniffling. It's going to be a very, very gross show. Before I start taking calls, I want to share some interesting bits of news I caught recently. And this actually happened last week. And I didn't get a chance to talk about it, but I really, really wanted to talk about it this time. I don't know how many spacecraft and missions we have eulogized on this program in our history. I believe we've done Spitzer. I remember we did Kepler. I think we did Cassini and Kepler, and now we're talking. I spoiled it. We're doing Spitzer now. The Spitzer Infrared Space Telescope. It was launched all the way back in 2003. Do you even remember 2003? That seems like a lifetime ago. And for some of you listening, it probably is literally a lifetime ago. And the Spitzer Infrared Space Telescope had 16 years focusing on the infrared part of the spectrum in complement to the work with Hubble, with the Chandra X-ray Observatory, with the Compton Gamma Ray Observatory. This was 4 satellites in orbit called the Great Observatories, each covering a different part of the electromagnetic spectrum. Infrared is really great for looking at dust, and if that doesn't sound exciting, then you're obviously not an astronomer, because to an astronomer, apparently the only interesting thing happening in the universe is dust. We are interested in dust for many, many reasons, mostly because when we are trying to study newly born systems, star systems that are just getting going, just starting to form planets, they're cloaked in layers of dust, which make it hard to look at with visible wavelengths, but infrared pierces right through, and we're able to look at it. And this is all near and dear to my heart. My very, very, very first research paper, not my first author paper, but my very first paper, I did a summer undergraduate program at the University of Rochester, working with Professor Dan Watson on the then recently launched Spitzer Space Telescope. And we were looking at newborn systems, and what we had found through our data and the subject of this paper were planets that were carving gaps in their protoplanetary disks. So when a star forms, it's surrounded by a disk of gas and dust. And as the planets form, they start to form gaps in there. And we could tell that there were gaps forming in these disks. And that's what we found. We were finding planets being born in the process of formation. That was such a cool project. It was a really cool paper. That was a really fun summer, and that was a long time ago. I went on to do absolutely zero infrared astronomy after that. But hey, you got to start somewhere. And that was a wonderful paper. And if you're curious, you can go to pmsutter.com/bio, my website. There's a link to all my papers if you want to read the paper. It's publicly available. That was just one of thousands of papers written over the past 16 years using data from the Infrared Space Telescope. And just because the telescope is down doesn't mean it's over yet. Data, it still needs to be looked at. It still needs to be processed. It still needs to be examined. People are still looking at old, like decades old Hubble data. So the Spitzer Space Telescope, even though it's down and it's just going to orbit uselessly until it burns up in the atmosphere and causes a headache for some future generation, probably crashing in the skies over Pittsburgh. Sorry, that's a joke involving last week. If, even though it's down, it's still going to produce science. So we salute you, Spitzer. You did a good job. That's the latest and greatest when it comes to space. But it's time to answer some questions. All right, space cadets, don't let me down. All right, what is my favorite color? Ooh, interesting question, Campbell Duncan. I'll answer that. First, there's going to be a lot of that. Man, you space cadets, this is the lucky stuff. Wow. Oh, solar orbiters. Yeah. A formation of the Earth. Oh. This is good stuff. All right, let's do it. This episode is going to take forever. You're hanging in with me. Anyone else? If anyone else has a cold, we can be cold buddies this week. We've got so many Space Cadet questions ready to go, so we're going to just jump right in because it is that kind of show this week. It's just too much fun. It's just too much fun to ignore the trusty Space Cadets and their gobs of questions that they lob at me every single week. We're going to start off with Campbell Duncan over on Twitch asking, hey, Paul, what's your favorite color? My favorite color is gray, but my favorite wavelength of light outside the visible portion of the electromagnetic spectrum has to be the microwave band, because the microwave band is where we see something called the cosmic microwave background. That is the background light emanating throughout the universe since it was only 380,000 years old. That is over 13.8 billion years ago. That light originated, formed, soaked, permeated, inundated the universe until it hit something like, I don't know, an infrared dish or antenna or telescope. And we can see it. It absolutely covers the sky. It is the number one largest source of all radiation in the universe. Something like 99.999% of all radiation in the universe comes from in the form of the cosmic microwave background. You could get rid of every single star, every single galaxy, and overall the amount of light in the universe would stay the same, because the universe was only 380,000 years old. It was a much more interesting place than it is today, capable of doing a lot more things than it can do today. So that's my favorite wavelength, is down there in the microwave. Also, it heats up soup. Not the cosmic microwave background, it's the wrong frequency, but different kind of microwave heats up soups and leftovers so you can do science and you can eat lunch. I mean, 2 for 1 in one wavelength. You can't beat that. Good luck with that, radio. Were you going to take ultraviolet? Oh no, you're just good for skin cancer anyway. Microwave for the win. Another question Orson Zed over on YouTube is asking, since planets migrate, do we have an idea about where the Earth originally formed? So check this out. Early solar systems are very crazy places. There's a lot of what we call planetesimals, which are newly forming planets but haven't really bulked up yet. There can be anywhere from a dozen to over 100 planetesimals in a young solar system, including our own. These planetesimals will crash into each other. They will wrap layers of gas and ices around them to be giants. They'll hang out in the around the sun and become rocky planets. It's a very, very chaotic place. We suspect that the rocky planets and the closer to a star like the sun are going to form in about their original orbits, or the orbits that we have today. That the where they form is where they are now. We don't think the inner planets migrate all that much. There is a big caveat to that statement that I will get to. But for the most part, we think the Earth formed relatively close to where the Earth is today. And same for Venus and Mercury and Mars. Now, the outer planets, the gas giant planets, that is a different case, especially when we look at Neptune and Uranus. Those are massive planets. They're planets that are also really far away from the sun. So how do you get a massive planet that far away from the sun when there isn't a lot of stuff out there? If there's not a lot of stuff, you can't build a massive planet. And according to all our models, as far as we can understand, in an early solar system, there isn't enough stuff way out in the orbit of Uranus and Neptune to make a Uranus and Neptune. So we think that these planets actually formed closer in. And in fact, all four of the giant planets formed relatively close together, somewhere between the orbit of Jupiter and Saturn. They were able to vacuum up enough material. And then Jupiter started to migrate inwards. And then Uranus and Neptune started to migrate outwards. There's also the possibility that there was a fifth gas giant planet that got kicked out of the solar system altogether. This process of migration of the outer planets kicked off something called the late heavy bombardment, because you're juggling with all the mass in the outer solar system and it starts sending comets flying into the inner solar system. It isn't a pretty time. But largely the inner planets remain unaffected, except in some star systems when you end up with a hot Jupiter. And I know that's a tease, but I'm going to tease into the break because I can, and you can't do anything about it. We are going to take a quick break, folks. I'm Paul Sutter. This is Space Radio. Don't forget to leave a voicemail, join the conversation. You can go to spaceradioshow.com for all the links. This show is brought to you by you. Go to patreon.com/pmsutter to learn how you can support the show, and I'll see you after the break. Incoming coughing fit. Oh. I will keep answering your question, Orson Zed. Protons have, how do they charge? Do they have charge polarization? Sun can compare the size of the farthest dwarf. Timothy Blau, have any brown dwarfs been observed to have satellites? Saw deeper energy how James see so far through the visible universe. Good question, Campbell. Yeah, good. Flip. Oh, love these questions. Yes. So many good questions. Thank you, Space Cats. And someone did a super chat. I saw some super chats here. Dobby Dazzler, so much. Thank you for that. That's huge. Big shout out. You're dazzling it today, Dobby. I love it. Here we go. Where was I? Space Radio. It's happening. When do I get to take NyQuil? That's all I care about. I mean, I care about science, and I care about space, and I care about you, space cadets, but I also want to know when I'm getting my next dose of relief. Isn't that crazy? Isn't that crazy about Uranus and Neptune? Put on a kettle and steam up your Orson Zed. Can you be come here and just like take care of me, like in a very practical nurse like way? All right, let's do this. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got more questions ready to go. But remember, you can join the conversation by leaving an online voicemail or by following the live streams. Check out spaceradioshow.com for all the links. And we are doing a Space Cadet Bonanza tonight, Thursday at 8 p.m. Eastern, where we do Space Radio Live. We've got Space Cadets, and yes, Space Cadets are warning. You may have heard I do have a cold, and I'm recording with a cold. I assure you it is not coronavirus, okay? I'm not in quarantine, okay? It's just a cold. I think. What are the symptoms of coronavirus? I don't know. Maybe I have. I don't think I do. I don't think I do. Let's just say I don't, okay? It's just a cold. That's what everyone said about coronavirus, I know. But forget it. Don't worry about it. This is a radio show. I'm not really in your face, so even if I had it, I'm not contagious to you personally. I was in the middle of answering Orson Zed's question about planet migration. The Earth and rocky planets tend to form where they remain, except every once in a while we're starting to see these systems where large planets just migrate all the way in. And by all the way in, I mean within the orbit of something like Mercury around the sun. So imagine Jupiter orbiting closer to the sun than Mercury. These are called hot Jupiters because, hot. And obviously, if you're going to send something like Jupiter into an inner solar system, if there are any rocky planets there, any little things like Earth or Mars, they are just gone. Gone, gone. Nothing can survive that kind of gravitational interaction and destabilization of a massive planet like that moving inwards. So either you get planets plunging into their star or just kicked out of the solar system altogether, in which case you just got a star and a hot Jupiter. Maybe there's some stuff left over in the outer orbits, but anything in the inner system is just done. Just done, and it's sad, but it didn't happen to us, thankfully. Moving on, we've got a question from, again, Campbell Duncan. I hear that Spitzer saw deeper than infrared than the James Webb Space Telescope, which is upcoming. Well, how will James see so far through the visible universe when it's looking so close to the visible light? So the Spitzer Infrared Space Telescope was tuned to a specific set of infrared wavelengths that let it study distant galaxies and dust in distant galaxies, new forming systems. James Webb Space Telescope, the next one, is going to be a very similar wavelength range. I don't know off the top of my head what the wavelength range of James Webb will be compared to what Spitzer was. But I do know they're both infrared telescopes. But James Webb is tuned to a very specific set of infrared wavelengths, as very, very special kinds of glasses on that will let it peer, again, to new forming systems, baby solar systems. It will look for exoplanets, and it will also look to very, very distant galaxies where their visible light has been so redshifted from the expansion of the universe that it's now down in the infrared. That is something that Spitzer couldn't really do, and this is something that James Webb will excel at. Excellent question. Philippe, I swear I can read. Philippe O on YouTube is asking, would there be any use for a fleet of small telescopes in low Earth orbit? Something like Starlink, but with telescopes. If you remember, SpaceX is launching dozens of satellites and then eventually thousands of satellites. to look at to hook up the world with internet access. And this is kind of annoying to astronomers, but kind of awesome for everyone else. And so there's an interesting debate going on. But what if we had thousands of telescopes? This is something that comes up in the astronomical community a lot. If we're going to spend a lot of money, which is better? Say one James Webb Space Telescope, or I don't know, 50 Hubbles. Hubble did a lot of great science. James Webb will do a lot of great science that Hubble could never do. Could we get a lot more impact out of 100 Hubbles than we could out of one James Webb? Overall, we think that one James Webb is worth 100 Hubbles. But what if we had 1,000 Hubbles? Or what if we had 10,000 micro observatories or digital cameras or some sensors or something? This is something that I'm sure is going to come up for discussion. I don't have an answer for you off the top of my head, but I'm sure this is going to come up in something called the decadal review. Every 10 years, the entire astronomical community in the US gets together and decides through a very messy political process what the priorities should be for the next 10 years. Like, what kind of questions are we really interested in as a community? What kind of telescopes are we interested in investing in? Creating a kind of roadmap. It doesn't guarantee funding for any particular project, but it does give like a stamp of approval. And so there's another one coming up this year, the 2020 Decadal Survey. And I'm sure there'll be a lot of white papers, a lot of discussions about fleets of smaller satellites, observing platforms. There are similar ground-based missions where we're using dozens of telescopes around the world to great effect, to study transient quake events, little bleeps and bloops and flashes that happen on the sky. We're using networks of radio telescopes. So it's very natural to think, well, what could we do with a fleet of satellites, of orbiting satellites, of telescopes or sensors? There might be something cool there. I'll be interested to see what comes out of the decadal survey process, to see, who knows? Who knows? I'm as curious as you are, Filippo. I really am. Sergio Botero over on YouTube is asking, is there a practical limit for Earth-based telescope size? For a single dish antenna, like a giant radio antenna, there's not really a limit. You can just build as big a dish as you possibly can. And that's more of an engineering and technology question rather than like a physics or astronomy question. To get around that, we build networks of telescopes that have, say, overlapping coverage or observe the same object at the exact same time. This is something we call interferometry. With this, we can have telescopes that are in effect the size of the planet Earth. It doesn't collect all the data as if we had a giant dish the size of the planet, but it still gets us something. And that's a very powerful technique. There are also considerations of trying to deal with atmospheric distortion, light filtering through the atmosphere, light pollution, and the bigger the telescope you get, the more you have to worry about these kinds of things. But we have plans to build telescopes 100 feet across, 30 meters across. And we can certainly build bigger in the future. It's just a matter of engineering and money. So we're not even near the limit of what we could build in the future. Thank you, Space Cadets, for all those amazing questions and more that I couldn't get to. We're almost out of time today on Space Radio. But before we go, it's time for the Blue Shift. Space Cadets, you are amazing as usual. And I do not plan on dying from this cold. Thank you. We got another super chat in. Passed by. I saw it. Bill Sugden. Thank you so much. And that's right. If you're going to give Fraser, give to me. He doesn't need the money. He told me, he said, Paul, Paul, I don't need the money. Tell everyone they can stop donating and contributing to me. I'm just filthy rich. I've got swimming pools full of $100 bills. I've got a vault with coins that I Scrooge McDuck dive into. You can just have all the contributions, Paul. Tell him. He said that to me. I swear. I swear. Here we go. There's no cheese tonight. Sorry. There's no cheese tonight. I do have a cheese, but I also have a cold, so I have like no sense of taste. And so I can't give you a very fair report of the cheese. So, but there'll be cheese next week. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get a little bit closer to you. And this is based on, what I want to talk about is based on a blog entry I wrote. If you don't know I blog, you can go to pmsutter.com/notes. And there I have the Ab Initio blog, where it's my thoughts on science and science communication and the relationship between scientists and the public. Really, really fun way to express myself and collect my thoughts. And I just recently made a post about scientists and science itself, how it's not just fallible, but science is mostly wrong. Most new results are incorrect. Almost all new results are incomplete in some way. There are mistakes everywhere. There are things that the researchers didn't think of. This is just a part of life. Like if you see like, oh, the majority of scientific papers published could not be replicated. Well, okay, like that's kind of the point. In science, we have no idea what we're doing. We're making it up as we go along. We don't have the answers. Nobody has the answers. So how can we be expected to get it right the first time if no one else is even asking these questions? Science is mostly blind alleys. Science is mostly bum results. Science is mostly mistakes. And we're also like, human beings. So we're going to make mistakes. We're going to miss something. We're going to have biases. We're going to have favorites. We're going to, we're just going to do all the normal human things. And that's fine. That's the point. The whole point of the scientific enterprise is to constantly cross-check ourselves and each other, knowing that we can't necessarily trust ourselves, knowing that we necessarily can't trust the results, knowing that we can't trust our colleagues. We can only keep checking and rechecking and rechecking. So yeah, most things published in science will be somewhere on the spectrum of wrongness, from just a few minor details all the way to out and out incorrect. And that's the way it is. That's the way it's supposed to be, because we don't know what we're getting into ahead of time. So the more mistakes we make, the more we learn, and the more we learn, the more science advances. Science advances through its mistakes. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter, and this show is brought to you by you. Visit patreon.com/pmsutter to learn how you can contribute. Thanks to Greg Moebius for producing, Nancy Graziano for wrangling the Space Cadets, and all the fine crew at WCBE Radio 90.5 FM in Columbus for making this show possible. Catch the live streams every Thursday at 8 p.m. Eastern. Visit spaceradioshow.com for more info, links to the live stream locations, and the episode archive. You can find me on social media. My name is at Paul Matt Sutter, and of course, thanks again, Space Cadets, for listening. See you next week. And remember, science is for sharing. End of transmission. We did it, Space Cadets. I'm going to get some humidity and some NyQuil. I'm going to call it a night. Thank you again, Space Cadets, and I'll see you.